All right, good afternoon, everyone. Thank you so much for coming. So thank you so much for coming today. This is going to be our third and final CaJAGWR seminar for the semester. This will complete 3 talks that we've heard about the binary neutron-star merger found by LIGO and also by a number of electromagnetic observatories earlier this year. Today's speaker, we're very happy to have Jocelyn Reed, who's come to us all the way from Orange County. She's a professor at Cal State Fullerton. She's going to be telling us about the physics of neutron stars, and in particular about matter in neutron-star mergers. Jocelyn, thank you so much for coming.
Thanks very much, Jonah. So I'll just try and stand over here. Can folks hear me well now? Okay. So yeah, so it's great to be up visiting and giving a seminar here. And I'm going to talk about the signature that matter has directly on the gravitational wave dynamics themselves during a neutron-star merger. So that's going to be kind of more of the gravitational wave story of this, of the GW 170817 event, rather than the aftermath of the electromagnetic observations. So just to give an orientation, partially to show off this cool video that a student of mine made. So when we're recording the gravitational waves from a compact binary, the gravitational wave signal is tracing out some of the dynamics of the source. It depends, as you can see, a little bit on the orientation that you're observing the binary, but typically the frequency that you're going to measure those fluctuations in the gravitational wave strain reflect the frequency of the orbital dynamics of the merger that's generating the wave. And that's the opportunity we have to learn about the interaction of the merging stars and measure their properties through understanding the details of the dynamics. So again, to set the stage, we can initially conceive of this system similarly to the way you might see a regular Newtonian orbiting system. A total mass, an effective mass of a orbiting system. And this energy, this is just sort of the Newtonian energy plus sort of elided post-Newtonian corrections here for the relativistic system, is modified by gravitational wave radiation, carrying energy away from the system. And as this energy is carried away, we'll have a decreasing radius and increasing frequency, and the gravitational wave tracks that orbital dynamics with the characteristic chirp. So the question then is how this chirp pattern depends on the characteristic parameters that describe the system generating the gravitational wave source. And the first obvious one to consider is the mass scale. So if you look at binary mergers of different masses, all at the same fiducial difference, and compare it to the strain sensitivity of, say, initial or advanced LIGO as a function of frequency, you'll see that the spectrum you observe from different merging objects depends most sensitively on the mass of those objects. So these are some of our sort of canonical systems going into the advanced LIGO observing run, where we have, say, 2 neutron stars merging, each with something like 1.35 solar mass a neutron star black hole, where sort of our old fiducial black hole mass was 10 solar masses. Black hole, these are all at the same distance, so the increasing amplitude here is coming from the increasing mass of the source system. And we also see that the merger of the objects starts to move towards the left to a lower frequency as the mass scale increases. Then you can just consider something like a 10 to 100 solar mass merger, or 100 to 100 solar mass merger, and you get this sort of characteristic sweep of the amplitude spectrum as you change the properties of the source. So although this shows the strain as a function of frequency, there's a very simple implication when we consider something in the time domain. So We're now in the habit of just, plotting out for these 5 binary black hole detections, the frequency versus time of the filtered data itself, showing these bright amplitudes of their chirps here. And for each of these black hole mergers, the time shown in these plots is less than 2 seconds. So each of these characteristic mergers here, all with masses greater than this red binary black hole shown, well, actually, I guess 1706, 08 is approximately the same mass scale as this. These are all coming through the LIGO band and merging in less than a couple seconds. So when we go to the binary neutron-star merger, we see immediately a system with fundamentally different characteristics. So this data spectrum shows almost 30 seconds of signal, and although this is a representation of the data that's visual for a human reading, we actually have a large amount of information about the signal in the 3 detectors, or at least in the Livingston and Hanford detectors, before this plot even gets being started to be made. But this shows that the gravitational wave time scale for this system is fundamentally different than what we'd previously observed for binary black holes. And then converting the recovered waveforms to a time domain representation emphasizes that, since compared to the time since 30 hertz of the binary black hole mergers, GW 170817 was visible for almost a minute after that representative frequency. So totally different mass scale, thousands of gravitational wave cycles sweeping through here from 30 hertz to over 1,000 hertz. And then the question is to try and figure out what we can actually learn about the source properties by mapping out the details of that dynamical in-spiral. So this is not done just with, so this is done for LIGO's analysis with sophisticated waveform models that can incorporate multiple layers of relativistic corrections, and now also tidal contributions from the matter in a neutron-star merger that allows us to compare waveform models through a high-dimensional parameter space, see how they compare to the data, and recover, for example, correlations here in an example binary black hole system between the 2 component masses based on the Markov chain Monte Carlo sampling illustrated in this movie. So this comparison is what allows us to determine things like the sky localization of the gravitational wave. So this is actually showing the long-term follow-up properties of this signal, not the rapid turnaround properties. So this is the sky localization figured out by the offline analysis, following up to get a localization here in green that's very compatible with the source galaxy of the associated optical emission. This particular sky area can be roughly interpreted as a combination of timing consistency between the Hanford and Livingston detectors, as well as relative amplitude consistency of the signal measured in each of the individual detectors. So the additional information from the low amplitude in the Virgo detector allows this timing circle from the Hanford and Livingston arrival time compatibility to be narrowed down to this final sky location size that was used to do the follow-up search. Of course, it's worth emphasizing that this analysis also indicated the distance to the merging neutron-star system, which is also really important in narrowing down the potential follow-up candidate galaxies. So this is just showing how that strain played out in the different detectors from the same sky localization. So here, the amplitude of the signal, so this is a neutron star signal. Our search templates don't include any merger physics in them. They're purely in spiral. They're also leading order in amplitude. So these are the amplitudes of the search templates, just these linear frequency power laws over the spectra of the three detectors, Hanford, Livingston, and Virgo, with the Hanford and Livingston amplitudes scaled to the recovered SNR of the search, and then Virgo extrapolated from the sky localization. So this Virgo, as you can see from a combination of the signal itself at that sky location having significantly lower amplitude, and the amplitudes, and the increased noise level in the early commissioning stages of the Virgo detector are what fed into that sky localization. So it turns out that the extrinsic properties like the sky location decouple somewhat from the intrinsic properties. So this is coming in from just the arrival time of the signal and the overall amplitude of those signal, and that's primarily generated by the early stages of the in-spiral. The huge swath of time as this neutron stars start quite far apart and in-spiral slowly through most of the frequency band. So that's going to tell us primarily things that depend on the chirp mass, a combination of masses that's really well picked out by our analysis. So this is a mass recovery plot showing that the masses of the smaller mass object and the larger mass object are constrained to lie in this sort of narrow banana window, which is picking out a particular combination of them very precisely. GW 170817 is compatible with an equal mass system of 1.36 solar masses, which is almost as generic a neutron star merger as you can imagine. And then you'll see here this variation here, the uncertainty in the mass parameters comes from the uncertainty in the mass ratio. So here, the red curve here is done with a measure of the spin of the components in the aligned with the binary or anti-aligned with the binary of less than 0.89, which is screamingly loud for neutron stars. But with this very broad prior on the spin, we do reduce the recovered spin parameters to show that this is the least spinning gravitational wave observed so far. But this is sort of an astrophysically uninteresting upper limit. It is showing that we are not having anti-aligned spins for the neutron stars, but this is a really quite fast spin parameter corresponding to something comparable to the fastest spinning neutron star, including accreting neutron stars in galactic binaries. If we impose a prior which is similar to neutron star binaries in the galaxy, we then basically recover again that it's not anti-aligned, but the aligned spin is recovering the prior assumption we make, and that tightens up the allowed mass ratios towards this equal mass system. So the analysis that you can consider in a sense astrophysically motivated is this restriction to spins observed in neutron stars in our galaxy with a good chunk of wiggle room for uncertainties in the equation of state and some additional spin up you could imagine. And that tightens up the constraints on the masses towards the equal mass thing. So I'm going to focus on this low spin parameter estimation when I start talking about the matter properties of this system. So as you've probably seen, we get a candidate system with masses, as I said, as sort of neutron star-like as you can imagine, although, of course, the merge remnant, not in a binary, is an interesting object, either the most massive neutron star or the least massive black hole we know about, but we're just not sure which. So let me then turn to the signature of neutron star matter in the gravitational wave signal itself. So this is seeing GW 170817 as a kind of an astrophysical collider. We've smashed these two dense objects together. Neutron stars on this QCD phase diagram are at relatively low temperature compared to our Earth-based colliders, and at very high density. So the cores of neutron stars may reach the density they reach is uncertain, but it may reach into these interesting phase regions. And then as the neutron stars merge, then they will go into higher temperature regions of this phase space. Then they throw off material that sort of, I guess, goes back towards the normal hadrons of our day-to-day life. And we see, in trying to extract the physics of this collision, we've seen a lot of discussion of the merger outflow properties, so the matter thrown off by the neutron stars and producing heavy elements and doing all that fantastic stuff. But we also have a probe of dense matter from the gravitational wave dynamics of the inspiral itself. And that's what I want to focus on here. So the specific signature of dense matter that comes into the gravitational wave signal is primarily from the cold equation of state of neutron star matter. So this is the equation of state in beta equilibrium, the pressure versus density relationship of matter when all reactions have been to proceed to an equilibrium state. And for neutron stars, the core densities are at or above nuclear density, shown in this sort of gray shaded region here. And there's a wide variety of proposed equations of state to describe that, depending on assumptions about the particle production, the energetics and interactions of the matter in its densest state. So each of these lines here can map to neutron star properties. For example, the mass-radius relationships shown here. Typically low pressures for a given density map to smaller radius, high pressures to higher radius, but we also have radius dependence with mass. We have different maximum mass relations, and we also have a different deformability of the star, which I'm going to talk about now, or in a little bit. So how does this actually feed into the neutron star merger? So we start off with this sort of post-Newtonian chirp. Here I'm zooming in on just the last 2 seconds of it. And for the first 60 seconds or 53 seconds, or whichever starting frequency you want to pick, the gravitational wave inspiral is indifferent to the presence of matter or the size of the stars for what properties of the masses and spins and other things you recover. So up to around 100 hertz, we have basically no signature of matter. For example, at around 100 hertz, if you have some sort of scenario like this crust shattering that Dave Singh and I once worked on with some friends who were actually here at Caltech at the time, you can transfer 10 to the 46 ergs in a fraction of a second at 100 hertz and modify the phase of the inspiral by 10 to the minus 3 radians, which is undetectable, at least for the next couple generations of gravitational wave detectors. So where you're going to look for the signature of matter is in the final milliseconds, fraction of a second of the waveform. So here I'm going to replace the whole inspiral here, and in particular this final panel, with something with matter incorporated into the model. So the first place to look is going to be just right here. So this is going to stay locked in place, but by the time you reach something like 400 hertz, you're going to see some small accumulated phase difference coming from the tidal interactions of the two stars as they've slowly inspiraled over the hundreds of orbits from this stage to that stage. And then you also have an entirely different scenario for the actual merger itself, where something like a numerical simulation is definitely required to capture something that happens after the stars collide, but it's also important to calibrate the final orbits themselves as the stars are interacting dynamically. So this final example of the final 30 milliseconds shown here. So this 30 milliseconds is these final orbits here where the stars begin to interact tidally. The tidal interactions modify the inspiral. Then the stars both are colliding and ripping each other apart, flinging off all the matter that's going to be observed in a kilonova. And this is one compatible scenario with GW 1708-17. There are other potential merger endpoints that could be considered. So everything, well, this final merger stage is not recovered in the gravitational waves, but this has been extrapolated from parameters measured by the inspiral into what might have happened. And then observations of the light curves can then give you additional constraints to tell you about what that final stage might have been. So the key, the first signature of matter on the inspiral comes from tidal deformations. So as the stars deform, there's some energy from the orbit going into the deformation, as well as the energy being lost to gravitational waves. So the result is that the neutron-star tidal interaction induces or polarizes each component star and accelerates the inspiral. So it makes depending on what framework you're in, it makes the effective potential of the two stars more attractive, or it takes additional energy into away from the orbit. And the particular size of this effect on the gravitational wave can be characterized by this tidal deformability parameter. So this is a combination of several macroscopic properties of the component stars, the radius of each star, the mass of that component star, each to the 5th power. So this effect is coming in to modify a term that's at effectively high post-Newtonian order. But this 5th power term here means that it's going to become important when the radius of the star is comparable to the radius of the orbit. This is not precisely extracting the radius of the star directly, because there's this other parameter here, K2, which is the love number of the stars. So the tidal deformability parameter is a combination of radius, mass, and love number. The effect of the love number here, it's something that can be measured in like satellites going around objects in our solar system, or trying to understand like the deformation of the moons of Saturn and Jupiter. But here it basically acts as a measure of how centrally condensed the stars are, which means that, say, a fixed radius with matter that's more centrally condensed will have a smaller impact from the tidal deformation in terms of the potential surrounding the star. So again, the impact from the equation of state here, the pressure-density relationship, is that as the pressure in the core of the star for a given density increases, the radius increases and the tidal deformability of the stars increase. So something like this extreme equation of state scenario gives a quite significant modification of the final orbits, although that one's now disfavored by GW 1708-17. So I made a big deal about the inspiral not being the whole story. We have the merger, and that's harder to see for this particular signal. But the merger dependence shows that compact stars compared to large stars, well, they run into each other at a certain point. That stops the merger. But they also have some acceleration here seen before they collide. These two examples also show some of the post-merger variety for compact stars that may collapse promptly to a black hole, large radius stars that are long-lived before they collapse. Although for GW 170817, the post-merger is hidden by the increasing detector noise at high frequency. That's something that may not need to wait for more than a generation of detector improvements to yes, work around. Oh, right, yes. So the other thing that you can do is compare the audio from these two scenarios. So I'm going to play you the chirps for compact stars and then the chirps for large radius stars. And perhaps you'll be able to hear the difference at the final frequencies here. So here's the compact stars. And then so that little whoop versus the whoop at the end is this sort of final stage here, having a slightly different audio representation. So the challenge, of course, is to convert your audio sensitivity to detector sensitivity so that that difference can be distinguished there too. It's worth pointing out that we talk about a Tidal deformability parameter that's generated entirely looking at the in-spiral properties of the star. It's actually modeled perturbatively to figure out how much a given tide induces a gravitational potential deformation to characterize that tidal deformability parameter. But empirically, we've found that this parameter also characterizes the merger. Certainly for equal mass systems, and now as some continued exploration has been done for unequal mass too, actually. So this is just showing that something like the frequency at the peak amplitude, something that is by no means a perturbative quantity, something that's describing the merger stages in as the stars collide and they are not being linearly perturbed and they are not far enough apart for post-Newtonian in-spiral to be at all an accurate depiction. Yet empirically, the properties of the merger are very well described by the same parameter that characterize the in-spiral. So this is, I think useful because it tells us that there's some quantity about characterizing neutron stars that can be extracted from the full waveform itself, although it means that there are possible changes of the equation of state you can conceive of which have no impact on this particular parameter and then would be invisible for the foreseeable future to gravitational wave observation. So here's an overview of the equation of state impact on a binary neutron star spectrum for the whole stages of the in-spiral. So this is pretty close to GW 170817. We're off by a proto% in mass. Unfortunately, I wasn't optimistic enough about the distance, but we also don't have fully designed sensitivity yet, so we'll just still wait for this particular one to come in. But this is just showing here for the in-spiral, there's sort of a regime where the signal is effectively point particle. There's a regime where the tidal effects become too significant, the neutron stars merge, and then there's this region after the merger with that final merged object oscillating, which can have additional gravitational wave emission. So this is something for a very canonical, sort of typical equation of state properties. If we make the equation of state properties more extreme, so the 2H equation of state that I showed earlier, this changes everything back to where the tidal effects come in. They come in at lower frequency. The entire merger is shifted, and the departures from the binary black hole equivalent are more significant. So I mean, plots like this have a weakness in that these are showing only the amplitudes of the gravitational wave, and it's the phase evolution of the gravitational wave that's really more relevant for what we can actually learn about these properties. Although it's not quite as pretty, I have sort of a quantification of the waveform impact here, looking at a quantity called distinguishable distance, which is basically the distance at which after which or beyond which the effect compared, so the difference I'm going to look at is indistinguishable in a gravitational wave detector. By indistinguishable, I mean that a waveform with and without that effect will have a difference smaller than the noise of the detector. So this actually shows that that in-spiral tide is more significant than it might appear just looking at the gravitational wave impact. So here we have 4 different chirp masses. This gray shaded region are the range found in our galaxy. I can first just look at the maximum detectable horizon distance with advanced LIGO. This is for design sensitivity. And that maximum detectable distance is something like this. If I take 2 equations of state, something that's sort of maybe more expected, something that's a moderately large radius stars with stronger equation of state effects, we see that for large radius stars over the entire region of neutron stars seen in our galaxy, we have a significant impact of the in-spiral tides on the signal. This is not guaranteeing that this effect can be measurable. Correlations can sort of obscure this kind of thing, but it means that it's a dangerous effect to ignore. It could induce systematic errors in other parameters, even if it can't itself be measured. For more typical equation of state, you still see that for nearby signals or for low mass signals, the in-spiral tides themselves are very significant to their effect on the waveform. These final sort of swaths here are going to quantify the systematic uncertainty in our description of the waveform effects. So these are taking 2 waveforms where I'm putting in the same masses, the same tidal parameters, but just varying the particular kind of waveform used to generate this. So this is 2 different post-Newtonian variations. This is a post-Newtonian versus an effective one-body variation. So this sort of tells you the level of systematic error in our waveform description in the description of the waveforms compared to the size of the effect itself. And you can see for low radius stars, at least as plotted here, the particular post-Newtonian choice you make, the particular waveform model you have is going to have a significant effect comparable to the size of the in-spiral tides themselves in the relevant range. And this is just the effect of putting a numerical merger on top of an in-spiral. So it's really the in-spiral itself is where most of this information is coming. So from this sort of in-spiral waveform model, there's this promise that neutron star matter can be learned about from a population of gravitational wave signals to some level of precision. So if you have neutron star mergers or a low mass neutron star black hole merger that's disruptive, that's going to give useful information about the neutron star equation of state. And since the neutron equation of state should be common to all neutron stars, we can actually stack information from multiple observations and pin down the expected properties of neutron star matter more precisely. So these are just some examples from the last couple years of people who have done this kind of thing. And typically what we see is after tens of observations, with randomly distributed waves in the sensitive volume, you start to get a meaningful distinction between different equations of state. So this was before 2017, and GW 170817 kind of disrupted this whole thing because it was screamingly loud for the first one, so it's sort of not really plottable on this scale, or not identifiable on these scales, but this is just sort of hinting at how the continued observation is going to feed into what we can learn about neutron-star matter. Many of these papers and references therein will carefully go through the sensitivity to different priors we make on the mass, the spins, and it's worth emphasizing that to do this precisely in a reliable way requires an accurate waveform modeling. So right now, we have a pretty good understanding of the first couple leading order contributions to the post-Newtonian framework. And we actually are getting to really remarkably accurate waveform from numerical simulations as well. So we have simulations that have tens of orbits. In particular, this Haas et al. Waveform has 22 orbits. And here it's compared to an entirely independent group waveform, which was aligned sort of before minus 13 milliseconds on the scale. And then they're continuing to trace each other nearly indistinguishably through to the merger. Well, not so much the post-merger, but at least now we're not so sensitive to this. So we're getting to a regime where our understanding of neutron-star mergers is fairly robust and fairly precise. And there's multiple, so this was done here, this is Japan, was in Germany. So there's multiple groups around the world who are beginning to agree on what the neutron-star merger waveforms will look like. This has enabled accurate waveform models that have been developed. So here's an example from 2017 where over the final stages of the stars approaching and merging with each other, we have an orange theoretical model agreeing precisely with the black in our data, at least up to the post-merger where there still are dragons. So now, unfortunately, when GW 170817 hit the detectors, this sort of waveform model was not yet implemented for our post-Newtonian, for our parameter estimation analysis. But fortunately, some people had been doing some interesting injection recovery studies before August that turned out to be very relevant. So here's one of the first studies from Ritika Dudi, Francesco Panarale, and others at Cardiff. And so what they're doing is injecting loud signals with different equations of state. These are actually TEOB inspirals hybridized with numerical relativity, and then recovering them with different waveform families, a typical black hole family, the simplified Taylor F2 post-Newtonian model with tides or without tides. And the first thing that they see here is that ignoring the possible presence of tides leads to biases in the recovered parameters. Here I'm just showing the chirp mass. The chirp mass will be skewed if tides are not allowed to vary and the injected signal has tidal effects. And that's, of course, more dramatic for an equation of state like this one here, which has a larger tidal deformability for each of the component stars. But more practically, Ritika also injected waveforms with different tidal deformability values and found that the Taylor F2 approximate actually recovered reasonably accurate values for the waveform deformability with this more sophisticated injection test. So this was one of the first indications we had that Taylor F2 could be an effective model for understanding neutron star parameters. Some additional recovery tests had been done earlier in the summer by Xiaoxu Liu at UWM, again showing injections here of a variant waveform model where a more sophisticated model was precisely recovered with a F2 waveform. So that's just to say that we think that the waveform systematics we have now are actually better than we might have feared at the start of the summer, because it turns out we have an effective post-Newtonian model that does a pretty good job. Now, we also have more sophisticated waveform models in development that can be used directly, but if I want to talk about results that we have published, I'm going to stick to this Taylor F2 analysis. So how did this play out for GW 170817? So this is a signal with the amplitude and chirp mass compatible with 170817. Here's Livingston noise. This is the amplitude as it hit Livingston's orientation. Here's design sensitivity. And then the final stages here have been replaced with simulation data, showing here the differences in the final approach from tidal effects as the stars in spiral. And then here we have the post-merger with different post-merger peaks, and you can sort of see kind of immediately that those are going to be small, at least for these scenarios, compared to the noise fluctuations in 170817 noise, although that's going to get more interesting if design sensitivity is reached. So this allows us to make constraints on the tidal deformabilities of the component stars. So here I'm going to show the deformability of the smaller star and the deformability of the larger star. And the parameter values that best match the detected data favor tidal deformabilities that are on the more compact side here, and disfavor less compact stars with large tidal deformabilities. So to sort of quantify this comparison, these gray bars are the equation of states predictions from the masses measured for GW 170817, using that equation of state to generate the tidal deformabilities of the component stars, starting at this equal deformability or equal mass limit, and then here these bars sort of sweep up as the chirp mass is varied, or sorry, as the mass ratio is varied for the system, the system considered in the sampling of the parameter estimation. So plotting them this way actually shows that there's a really clean separation between all these, well, this is maybe not so clean, but here there's a very clean separation no matter what mass is compatible with the signal. It's outside this 90% contour of the samples from GW 170817's deformability recovered. So we can then say that stars, that equations of state that have these large tidal deformabilities are disfavored or ruled out by the data. And these particular examples have radii for the neutron star of around 15 kilometers. This one actually tracks kind of closely along the contour. So these contours are these kind of diagonal swaths because there are some correlations in the data from one star being more tidally deformable versus the other star being tidally deformable. There's sort of a chirp tidal deformability that's going to be these diagonal slices here. So this equation of state H4 is roughly along our 90% contour level, and that's a star with roughly 14-kilometer radius for this 1.36, 1.36 case, or 1.4, 1.4 case. The radius is about the same in both of those situations. The samples that we favor are tighter in around 11 kilometers, where we have some very common equations of state like the Sturm-Liouville model or a Akmal-Pantara-Pandey and Ravenhall number 4, which is all the... so these equations of state are more compatible with the data. And at the sort of 50% or 90% level, we can't rule out, say, a binary black hole system here, although there's some, this is just the first analysis, and there's additional work being done. So we'll see if it remains buried in noise or not. The more compact stars are more difficult to distinguish from binary black holes because the effects go to higher frequency, and then our detector sensitivity gets worse. Now, from the rates we had, so here's in these black bars are different kind of rates predicted for different merger-related processes like GRB progenitors or our process sites. And here's sort of a rate compendium predicted for advanced LIGO in 2010. With the first observing one we'd ruled out this right-hand region. Now with GW 170817, we have sort of an upper limit here, a lower limit roughly here. There's still a pretty big spread here because one signal is not a good population. But this is definitely suggesting that the future is bright in terms of how the number of signals observed in advanced LIGO will line up with some of these hopes from, to say, almost a decade ago. So certainly 40 per year is very compatible with the data so far. So what could we do with something like that? Well, 40 events, this is from Lackey and Wade 2014, that allows us to start pinning down precisely the radius of neutron stars if we do something like assume a fiducial equation of state model describing both stars and see how that, well, this is a parameterized equation of state model describing both stars, and seeing how the data from all the events together constrains those equation of state parameters. This is an example showing that for the different densities of the matter inside the neutron star, we may end up with a large number of events with pretty tight, these are 95% region constraints, that would rule out a large family of equations of state. So the future possibilities are bright, and I will stop here and answer any questions. Not necessarily. So this is a standard problem with modified gravity in neutron stars, that there you can modify the gravity or you can modify the neutron star matter, and many observations can't really tell the difference between them. So this has all been done assuming GR. And then, you know, when LIGO does tests of GR with something with neutron stars, we have to be careful that the model or the region of the waveform that you examine should be not in this region where uncertain matter properties are affecting the signal. So, for example, we know that the matter properties have this, well, it's a 1 over r to the 5th scaling. So as the stars are more far apart, then it becomes negligible in a very generic way. So tests of gravity with something like this signal would focus on the low frequency regime, where this thing, it should be, for all conceivable values, not significant. Yeah.
So if it was hard to tell, based on the parameters, whether it was compact enough to be binary black holes or not, what was it that tipped off LIGO that it was neutron stars and not just really small black holes?
Well, I mean, the optical emission was probably in practice. So based on, like, if all we had was the gravitational wave, It would probably been more of a fight to call this a neutron-star merger with all the collaboration signing off. Really, it was the masses, though. The fact that these, and to be, we don't know that the companion to the Hulse-Taylor binary is a neutron star either. So at a certain point, these things are called neutron stars, even though we're not entirely certain that all of them are. But yeah, so the mass is really the key indication that classified this as a neutron star merger. And, so being more, definitely more, being more speculative, we do see things like, I guess that's not public. So as we continue analyzing the signal, you can start to say, so you see this distribution is somewhat pulled away from zero. We do see that if you ignore matter properties, you skew other parameters. So if you ignore matter properties, what you would get would be other things would try and accelerate the merger, like anti-aligned spins. That seems a little weird astrophysically. So it's very consistent with the neutron star picture. But to be very precise, we can't rule out a binary black hole from the gravitational waves. Yeah.
The 817 event was found from a particular place in space. Is there anything special about that particular place? And if you were looking for more events, would you look for something like that place? What's the criteria?
Yeah, so it wasn't a particularly special place on the sky. So each of the detectors, has an antenna pattern with more sensitivity. But Virgo was near a null in its antenna pattern, and the two LIGOs were, I guess. I don't think they were, particularly special for that location. And then, of course, the Earth is spinning around anyway, so we're sort of sweeping through the sky. So I think just the continued operation is going to be very generic in terms of sky location, and there's no reason to expect this was a special sky location.
Post-merger spectral beams are those? Yeah. You just answered my question. They depend on the equations.
Yes. Yeah, and actually, so this one is a disfavored one now, the one that's in dashed lines. So we're pushing, unfortunately, our compact in-spiral constraints are pushing the post-merger into the harder to measure parameter space. So there's sort of a reason there were Hirby dragons for the post-merger modeling. So it's hard. So there's a number of challenges, and well, anyone who does numerical relativity can kind of also back this up. But as the stars collide, the convergence of the waveforms tends to be not there. So you're sort of okay until they collide, and then it's very hard to get a convergent agreement of the simulation resolution. Then you have so then the post-merger signal can be fairly simple. There's some beating. There's usually sort of characteristic frequency peaks there. It has semi-exponential die-off. It lasts for tens of milliseconds. You can sort of do some generic stuff. I think James Clark is kind of the expert of how to consider what could be extracted from the gravitational wave signal. But my understanding is you really want to do sort of a pretty generic burst search for that kind of transient burst search for that kind of signal.
There's been some work looking into nonlinear like this. Could you comment on what it is to
Yeah, so there's sort of interesting, so this is the leading order linear tides. There's some interesting mode couplings. So I talked about this cross-shattering mode that could transfer a huge amount of energy. There's also, so that's also a linear mode, but there's also this work by Nevin Weinberg and collaborators at MIT showing that when you consider the full spectrum of modes in a neutron star, you could get some couplings, the nonlinear couplings between modes on different scales that could take energy away from the in-spiral at earlier frequencies. So I guess like the first step we have is from this observation, we have some limits on how much that process could take energy away. And I think Niels Andersen and Wen Ho have some early preprint on the archive kind of trying to quantify that from the fact that we detected this signal. One of the big challenges with that kind of thing is there's not really a numerical prediction for the amplitude of the nonlinear tide energy extraction. So you can sort of get order of magnitude, but there's like a bunch of order of magnitude for what frequency it is, what amplitude, how many modes there are. So there's so many uncertainties that it's not a good predictive model, I guess, but it's something that we can start to constrain. And then it would be tricky to map back to the actual properties of the equation of state through that, but I'm sure it's something that it's tricky because you know, the time scale to do a full analysis of that, this is happening in the early in-spiral, so sort of a tidal forcing of a neutron star where you have to resolve the composition to have buoyancy for some of the modes involved, as well as just a lot of physics to put into the system. Yeah.
In neutron stars, how big is the effective universe? And specifically, if we're thinking about if you have dark matter and particles interacting, quickly interacting, can that modify the waveform? And so we can see, could you be able to think about this?
So, I mean, I think we're assuming the matter's in beta equilibrium, so that I believe I imagine people have looked at this in more detail. I think people have looked at sort of usually like the dark matter density is too weak or is too low for there to be some significant coupling. There are things like some scalar instabilities where the curvature in the neutron star can couple with scalar fields in alternative theories of gravity and spontaneous scalarization kind of scenarios. And it's one of those alternative theories of gravity that ends up being degenerate with the neutron star equation of state if you're looking at isolated neutron stars. So there are some explorations of these kinds of things. I don't know actually for dark matter particularly, but I think for the typical expected densities, I think it's not a big interaction, but maybe for more speculative things it might be interesting.
Okay, so we do have some wine and cheese outside. I think Jocelyn gave a great talk today. Let's thank her for coming up here.
Very nice.
Thank you. How are you?
Okay, how are you?
Good.
Better now.
Can I ask you a little bit question? So now you show the tidal deformability, and what kind of nuclear parameters like incompressibility, like density dependent symmetry, can we put some constraints?
Yeah, so it's very similar to the neutron star radius. So something like the density dependence of the symmetry energy is really what feeds into that kind
So you show the kind of combination between the radius and the mass. So that's why